So I'll now move away from the depth profiling and on to the last topic I'm going to discuss today. So this is going to be focused on confocal photoluminescence and both steady state and time resolved, and how that can be applied to solar cell characterization. So analysed here perovskite solar cells. Most of the audience here is probably familiar with these already, but because this is kind of a broad introduction to confocal PL and Raman, or give an introduction to these materials for those of you not familiar. So they're named after the Russian mineralogist, Count Lev Alexeyevich von Perovsky. And in the broadest sense, any compound that obeys the ABX-free crystal structure shown here is a perovskite. However, the kind of boom in research in these materials and why they have received so much attention is these so-called hybrid perovskites, where you have both inorganic and organic components, with the archetypal one being methylammonium lead iodide, as shown here on the on the right. So you've got methylammonium in the center. This is your organic component, surrounded by inorganic octahedra of iodine and lead. And these have had a boom in research because they have very high solar cell efficiencies, and they're also now been investigated for other applications, such as laser gain materials and light-emitting diodes. Photoluminescence is a powerful way to investigate these materials because when you excite the perovskite, you promote electrons from the conduction band to the valence band, from the valence band to the conduction band, sorry. This is the same process that occurs when these solar cells are illuminated under the sun to generate electricity. And so the behavior of these when they're excited is important to their solar cell performance. You can either look at the intensity of this decay back to the ground state, generally higher PL intensity, higher solar cell performance, and you can also look at the lifetime. And these solar cells typically consist of multiple layers in order to get optimal performance. And that's what we're going to focus on in this final section of the talk, is investigating these different layers. So the perovskite solar cell structure that I want to introduce to you for this section is shown here. So as an ITO glass, and then deposited in the ITO glass is carbon nanotube towers. And the idea of these is to act as a hole extraction layer. So you generate charge carriers in your perovskite, so electrons and holes. And to get a good solar cell, you need to get the electrons to go to one of your electrodes and the holes to go to the other. And you typically do this with the aid of other layers to pull the electrons and holes out of the perovskite. So here we have P61BM to pull electrons out towards the silver electrode. And in this paper, they were looking at carbon nanotubes to pull the holes out. And we want to investigate how good these carbon nanotubes are at extracting holes from the perovskite. Just a different image so you can see what this looks like. This is taken from the paper, so we were a collaborator on this paper. If you want more details, you can see the paper in Advanced Material Interfaces. But the idea is that you've got this pattern substrate on the ITO with vertically aligned carbon nanotubes. This is an SEM image just to show what these carbon nanotubes look like. And now I'm going to show how confocal photoluminescence microscopy can be used to characterize the properties of this perovskite carbon nanotube layer. So shown on the left here is a real picture now of this patterned carbon nanotube substrate. And this is taken with a reflected dark field image. So white light illumination and looking at the reflection of that white light back to the camera. And you can see the pattern. So that each of these little squares corresponds to an island of vertically aligned carbon nanotubes. And then this dotted structure on top of it is the perovskite. And it looks grainy because perovskite typically deposits in different grain sizes, which is responsible for these black dots. So now is the same substrate, but we've imaged it using confocal photoluminescence. So here the perovskite was excited at 532, so below its band gap. Electrons electrons are promoted from the valence band to the conduction band, and then they decay back down, releasing light. And so regions with high photoluminescence are shown in the bright yellow here, and regions of low photoluminescence are shown in the dark. And so what this is really given as a measure of is how efficiently electrons and holes are being extracted. So to get photoluminescence, the electrons and holes need to recombine within the perovskite. And you can see this is occurring in regions where we have bright intensity. Where we have the carbon nanotubes, the holes are being extracted by the carbon nanotubes, and therefore they can no longer recombine with the electrons. And you get this drop in the PL intensity on top of these carbon nanotube islands. So this is direct proof that, or at least an indication that we've got efficient hole extraction out of the perovskite layer, because you can see this drop in PL intensity occurring on top of the carbon nanotubes. And just if I show this in a spectral comparison, so one thing I should make clear with all these maps is each of these points, to make this map, corresponds to a spectrum. It's not simply intensity imaging. The intensities are post-processing. In the Ramico software of the RMS 1000, you can extract the spectra from every point in this map. So here I've extracted it at one of the bright regions, so you can see high PL intensity, and at region 2, lower PL intensity. So if we look back here to the dark field image, there's one question that might arise, is that how can we be sure that this difference in PL intensity we saw is due to hole extraction and not simply due to the amount of perovskite sitting on top of the carbon nanotubes? So you could argue that the way perovskite deposits onto the ITO and the carbon nanotubes is different, and you might have less perovskite here, and this might be responsible for the photoluminescence decrease. So we would really like a complementary measurement technique to confirm this hypothesis that it's due to hole extraction. And the answer is to use photoluminescence in lifetime imaging to do this. So for those of you who do photoluminescence microscopy, you're probably very familiar with this. For those of you who come from the Raman side, you might never have heard of TCSPC. So I'll give a brief overview. So we can image the photoluminescence lifetime using a technique called time-correlated single photon counting. And the idea here is the laser fires, excites the sample. When the laser fires, it sends a trigger pulse to the electronics, which starts a clock. And the photon from the sample is emitted and detected by a PMT. And this is converted to an electrical pulse that stops the clock. And so the idea of this measurement is you measure the difference between the start and the stop time. And then you build up this in a histogram. So if you measure once, you get a single point on this histogram corresponding to a certain time it took for this photon to be emitted. You then fire the laser again. Another point is added to the histogram. And eventually you build up the entire photoluminescence decay using this technique in order to get the photoluminescence lifetime out of the sample. So the RMS 1000 can do confocal photoluminescence lifetime imaging. So our Edinburgh Instruments picosecond pulse diode lasers could be mounted into the RMS 1000. So this is a pulsed light source, and that's used to do the lifetime mapping. So I'll show you here an example of this. So this is the same perovskite carbon nanotube sample, but now we've zoomed in here just to look at 4 squares. So this is a transmitted bright field image. And now if we excite the sample and measure the lifetime, we get this photoluminescence lifetime image of the sample. So regions that are shown in dark here have a low average lifetime, and the regions that are brighter have a higher average lifetime. And if I show that, again, you can extract the lifetimes from each point. So here what we did was we measured the lifetime, so the PL decays at every point on this map, and then fitted these decays with multi-component exponentials, and then calculated the average lifetime to get this color plot here. And this shows that in regions where the carbon nanotubes are present, the lifetime decreases, and that can be seen here in this lifetime plot, the decrease in lifetime compared to the bulk sample as when you're on top of the carbon nanotube. And this is what we would expect if we're getting hole extraction, because if holes are being pulled from the perovskite, then they can't emit photoluminescence, and the lifetime should therefore decrease. And so this gives complementary information to our confocal intensity imaging that these carbon nanotubes are acting as hole extraction layers in the perovskite. That brings me to the end of my talk today. Thank you very much for your attention. And if there's any questions